Right. Welcome to IIT Bombay's virtual commutative algebra seminar. We are very happy to welcome Professor Eloísa Grifo from University of Nebraska at Lincoln. Today she will speak on a survey on Harbourne conjecture. Her talk will be for 60 minutes and then we will have question answers. During the talk, you can, of course, ask your questions in the chat box and one of us will relay it to her. So over to you, Eloísa.
Okay, well, thank you so much, both all of you for showing up today and the organizers for inviting me. I've always wanted to visit India and I still haven't had a chance to do it, but it's very nice to be able to be in India virtually. So let's see, what I want to do today is I want to sort of survey one of my very favorite conjectures, which is Harbourne's conjecture. And maybe let me give you a spoiler alert already. This is a conjecture that isn't true in its original form, but I think in a way that's part of the reason why I like it so much. It's a story full of twists and turns, and by the end of the story, I hope to convince you that in some sense this is a conjecture that is mostly true, and it has sparked a lot of really interesting research that I want to tell you about. Now, it is hard to completely tell you the full story in 60 minutes, and I know I will fail to tell you the entire story. There are pieces that I'll have to leave out. So I'm sorry about that, but I'll try to tell you as much as possible in the time I have. Now, if you maybe some of you were here for the very first talk in this seminar. So the very first two talks back in 2020 were given by Craig Hunicke, and one of the topics of his first two talks was precisely symbolic powers, and that's the topic I want to tell you about today. So throughout my talk, I'm going to always be assuming that I have a regular ring. And to be completely honest, the story I'm telling you makes sense, and it's also an interesting story without the assumption that R is regular. But the point is that it's a difficult technical story, and even in the setting where R is a regular ring, it's already a very interesting story. So I might as well make this assumption. And I'm also going to assume that all the ideals that I write throughout the talk, they're always going to be radical ideals. And again, we could talk about a more general version of everything that I'll say, but the case of radical ideal is already interesting enough. And if I don't assume the ideal is radical, there's actually two different possible definitions for symbolic power. So the technical details would get more messy. So I'm always going to stick to this assumption. So what are these symbolic powers? You give me your favorite radical ideal I, you want to compute its n symbolic power. What I'm going to do is I'm going to look at the ordinary power I to the n, and I'm going to write a primary decomposition for it. And I'll look at that decomposition, and I'm going to collect the components that come from minimal primes. Notice that I'm assuming that ideal is radical. So the minimal primes and the associated primes of I are really the same thing. So I'm collecting the minimal components of this power and throwing away the embedded ones. So, for example, when you have a prime ideal, what I'm talking about is the ideal of elements on my ring that live in a power after I localize at P. So the things that are sent inside the power, perhaps by something outside of P. So there are many reasons why you might be interested in studying symbolic powers. For starters, because maybe you care about primary decomposition. But there are also geometric reasons why one might want to study symbolic powers. And so one of those geometric reasons is this classical result of Zariski and Agata. And I like to think of this as sort of a higher order version of Nussel and Zatz. Right? Nussel and Zatz would tell me that my ideal I is the set of polynomials that vanish on the corresponding variety. So it's the intersection of the maximal ideals that contain my ideal I. The Nagata says that n symbolic power is what I get when I take that intersection of maximal ideals, but I raise each maximal ideal to the nth power. And maybe let me already say immediately, of course, that powers and intersections don't commute, right? So what I'm writing is a priori not the nth power. But this is telling me that the polynomials in the n symbolic power are the things that vanish to order n on the variety that I defines. So this would be a geometric reason why maybe you would want to find things about who's symbolic power. And so with that, so I as I said, I pre-wrote a few of the things in the talk because I was concerned about time. So I'm going to go a little faster. And if you've never seen this before, it might be a little too fast, and I apologize for that. So here's some quick properties of symbolic powers. If you think about it from the perspective of things that vanish to order n on the variety that I defines, maybe that makes these very intuitive, that these should be true. But of course, you can prove all these properties easily from the definition. So, for example, the n symbolic power of an ideal always contains the nth power. And when you take a higher order symbolic power, it's contained in a lower order symbolic power. So things that vanish to higher order also vanish to lower order. And now if you take a product of two different symbolic powers, that's something that lives inside the symbolic power with whose order is the sum of the orders. So if you like, this says that this family of symbolic powers, this is a graded family of ideals. And whenever you have a graded family of ideals, something that satisfies something like this, what it can do is you can take your family and construct a graded algebra from your family. So what you can do is you can take all the symbolic powers and stack them all together and make this graded algebra, where the T here is just keeping track of degrees. It's saying the thing that lives in degree n in this graded algebra is the n symbolic power of I. And here's something that maybe, if you've never thought about this, that maybe will call your attention to the fact that symbolic powers can be very difficult to study, is that this algebra here is not, so this is called a symbolic piece algebra of I, and this isn't necessarily a finitely generated algebra over R, or equivalently, this isn't necessarily an Adarian ring, which means, when this isn't finitely generated over R, that is saying that you have arbitrarily high symbolic powers that have, let me say, sort of unexpected things that aren't just coming from the lower order symbolic powers. And I might make a couple more comments about this. The topic of today is not symbolic piece algebras, but I think that's an easy thing to point to show you how technically complicated symbolic powers can be. Now, I said these aren't the ordinary powers, but they sometimes are, of course. So they contain the ordinary powers. They are, maybe let me say immediately, they're difficult to compute computationally. Even if you have a really nice computer, it can be really difficult to do computations with symbolic powers. But they at least contain the ordinary powers. So it'd be amazing if they were the ordinary powers, because you would know then who exactly lives in the symbolic power. So at least when your ideal is generated by a regular sequence, or if you like, when it's a complete intersection, then all the symbolic powers are in fact the powers. But I want to point out two things. First, this isn't an if and only if, right? So there are many things that are not generated by regular sequences whose symbolic powers are the powers. But also, the general thing you should expect is that they're not the same. So let me compute an example, at least, just to to give you some sense of what sort of things may happen. And there are many nice examples to do. I'm going to show you one of my very favorite examples to do in a talk to show people. But it's also in part an example that might feature later in the talk. So let's say that you give me a prime ideal. I want to remind you that this is a description of the symbolic powers. So I want to speak about a particular prime, and I wrote it in a somewhat, I was going to say unconventional, not quite unconventional, but this isn't quite correct notation. So let me tell you what I mean. I'm sending x to t cubed and y to t to the fourth and z to t to the fifth. So what I'm writing here is I'm writing the defining ideal of the curve that's parametrized by t cubed, t fourth, t fifth. And that ideal, you can compute with Macaulay, you can try computing it by hand. You're going to find that it's a 3-generated height 2 prime ideal. And here are 3 minimal generators for this ideal. Now, I want to convince you that the symbolic powers of this ideal are not the same thing as the ordinary powers. And so to do that, let me look at the element. Oops. So let me look at the element f squared minus gh. Okay, where f, g, and h are these generators I gave you. Now, without doing a lot of computations, if you just stare at it for a minute, I think you'll convince yourself that when you write f squared minus gh, all the terms that don't have x are going to be killed off. So this is an element that is actually x times something. So this q here that I wrote is a q that if I really wanted, I could write who q was very explicitly. Right now, I've given you an implicit equation for q, but I will not need to know who q is explicitly for what I'm going to do, but I could write it carefully if I wanted, okay? But my point is this element, x times q, is something that lives in the square of p. But on the other hand, this element x is not in p. Right? For example, because x does not vanish on this curve t cubed, t fourth, t fifth. And so just from the fact that I found something not in p that sends this thing q inside of p squared, that tells me by definition, if you stare at the definition up here, that tells me that q is actually something in the second symbolic power. However, I claim that this element q is actually not in the square. And the easiest way here to explain that this q is not in the square of p is to count degrees very, very carefully. And what I mean by that is this ideal p that I gave you is not homogeneous. It's quasi-homogeneous. And to make it homogeneous, I have to set the degrees of my variables to be the degrees of the things they land on. So I'm changing the degrees of the variables from the usual ones to 3, 4, 5. With this, my ideal is homogeneous. And with a quick mental computation, I think you'll see what I mean. I'll say quickly that this is an element, is a homogeneous element here. And its degree is actually 18. Because, for example, f here has degree 9. And so f squared at least has degree 18. And then you'll see that gh also has degree 18. These have degree 10 and 8. So without me having written q explicitly, I immediately note that I know that x has degree 3. So automatically, whatever this q is, I know it's something of degree 15. On the other hand, if you look at your ideal p, so I said this out loud, this f has degree 8, and sorry, not degree 8, this f has degree 9, this g has degree 8, and this H has degree 10. And so that tells me that the smallest degree of something in P is 8. And so the smallest degree of something in P square is 16. So there isn't anything that lives in my P square that could possibly be an element of degree 15. So simply by degree reasons, this element Q is not in the square. Okay. So at least the square of this ideal is not equal to the second symbolic power. And in fact, it follows from a theorem of Craig-Hunicke from the 80s that all the symbolic and ordinary powers of this prime are all different, except of course for when n is 1. Let me point out, however, that by the properties that I wrote above, the square is contained in the second symbolic power. I'm simply saying they're different. And let me point out without any proof that in fact, if you went and looked at the third symbolic power, so the next symbolic power, it becomes a smaller ideal. That would be small enough to be contained in the square. And I'm writing this to foreshadow where I'm going. The thing I really want to tell you about today, the topic of today, is a question known as the containment problem. And I think, I did not write. Okay, that's good. Sorry, let me just organize my things here. Fantastic. Okay, so what I want to really talk about today is one of my favorite problems. Oops. And the reason it's one of my favorite problems is that it's very easy to tell people what the question is, but it's a very difficult question. And I think it's nice when you have a question that you can easily describe to somebody, easily give them a sense of why you want to know the answer, but that that sparks lots and lots of interesting research. So roughly speaking, the containment problem is the following. You hand me your favorite ideal that, remember, to me is always radical. And I want to find which symbolic powers are contained in which powers of my ideal I. This is what I want to answer. And I want to answer this question from a best possible perspective. Notice that if you hand me an A and a B that works, of course you can make the A bigger, and I can make the B smaller. And, the statement still remains true. So what I really want to do is, given a B, I want to find the smallest A for which this is true. And it's not clear yet even that this always has an answer, right? This doesn't always have an answer in full generality, but with the conditions I've put down today, this does always have an answer. Maybe let me say quickly that back in, back in the few decades ago, so maybe between maybe mostly in the 80s, there was maybe when the interest in questions like this started, and in particular, Schenzel studied the question of when you can always answer this. Of course, I'm rephrasing what he was studying to maybe an easier format to what we're saying today. But so let's say that I go and try to answer this question. I want to point out to you that this question is actually secretly a bunch of different questions all put together. So for starters, if you could make A and B be the same number, so suppose you could prove that the n symbolic power is contained in the nth power for a particular n. We already know that backwards containment is true, right? So that would automatically tell us that the symbolic and ordinary powers are the same. So secretly, this question is asking me about the equality problem, right? It's asking when the symbolic power is equal to the powers. But it's asking more. If the answer is no, they're not equal, it's asking for some comparison between them, right? It's asking how far away from the ordinary powers are the symbolic powers. Now, this also contains a very classical, maybe more geometrical question. Now, remember I said in the beginning, of a polynomial ring, the symbolic powers are the polynomials that vanish to order n on the variety that the ideal defines. So it's a natural geometrical question to ask, what are the degrees of polynomials that vanish to order n on a given variety? And if you want to study that question, if the hardest thing to do is to give lower bounds on the degrees of those polynomials vanishing to higher order. And if you have answered the containment problem, or at least if you have partial answers to it, if you have containments that are true, you can give bounds on those degrees. So suppose you knew that the asymbolic power was contained in the bth power. Now, typically we write smallest degree with an alpha, but because I'm not going to need that notation for the rest of the talk, maybe I won't introduce it. I'm just going to tell you the smallest degree of something non-zero, right? Otherwise, it's not interesting. And the asymbolic power would automatically be greater or equal than the smallest degree of something in the bth power. But of course, the degree of something in the bth power is b times something. B times the smallest degree of something in I. So once you prove containments like this, or variations on this containment, you are in particular in a position to give lower bounds on degrees of things in symbolic powers. So these are just some of the questions that are secretly hidden inside of the containment problem. Now, I said that I'm talking about regular rings today. And for regular rings, we have a beautiful answer to this question. It's one of my very favorite theorems, not just because of what it says, but because it has beautiful proof. So this is a theorem that was first proved, over C by Ein, Lazarsfeld, and Smith, using the theory of multiplier ideals back in 2001. And then soon after, Hoxter-Hunicke did the case where your ring contains a field. So again, a regular ring contains a field. And what they did was they used characteristic P techniques to prove it in characteristic P. And then reduction to characteristic P to do the case where your field is characteristic 0. And that left the mixed characteristic case to do. And that was recently solved by Mann and Schweid using perfectoid spaces techniques. It's a theorem that's now officially from 2018. And they basically developed a mixed characteristic theory of multiplier ideals. And then once you have the right theory established, it's easy to apply the Ein-Lazarsfeld-Smith proof from the characteristic 0 case. So what does the theorem say? It's going to give me an answer. It's going to give me containment. And I stated in the beginning my rings were all regular, but maybe this time I'm going to write, and maybe I'll add in the word excellent because the Schweid result needs that. Maybe let me put excellent in parentheses. This is just to remind us that this only applies for regular rings. I'm only talking about regular rings today. So I have an excellent regular ring, and I want to write a containment that is true for all radical ideals I. And I'm going to need a special invariant of I. I'm going to call it H throughout the talk. And I'm doing this to save myself some time. So H was going to keep appearing, and I won't keep I'll maybe remind us as much as I can that H is the big height of I. But I'm basically saving the letter H from now on to only mean this. So if I write H, I mean the big height of I. And what that is what I get when I look at the heights of all the associated primes of I. And I take the maximum instead of the minimum. So I think of this as a more honest version of the height, right? The height would only look at the minimum of these heights instead of the maximum. So this is the invariant I'm going to need. With this invariant, the Hn symbolic power of my radical ideal is contained in the end power for all n. So in particular, let me point out that as a consequence of this, if you knew, let's say, the dimension of your ring, then the nth power, symbolic power, will be contained in the nth power for all n, which is particularly nice because it means that there is a uniform containment among all radical ideals, right? We're using something here that does not depend on I. Now, I'm only talking about regular rings today, but I'm going to allow myself a couple of minutes to make a few quick comments about this. So first of all, before this, shortly before this, in 2000, is there a question? I heard a little.
Yeah, there's a question from Miyazaki. I'll just read out to you. The definition of big height runs through all minimal primes if the ideal is not radical.
Actually, I think the typical thing to do is to go over all associated primes, not just minimal primes. And in fact, that's what you're going to do for the general version of this. But big height also appears in other contexts besides symbolic powers, and you really want to take associated primes.
Okay.
Good question.
Thank you.
Okay, so yeah, you're welcome. So let me make some quick comments. Notice this is saying that the answer to the containment problem is linear in a way, right? If you think of this as what is the function on n that you can put up here, the best possible function, is saying that that is at most linear, that there is a linear function on n that works. And shortly before this, back in 2000, Irina Swanson had already proved, roughly speaking, that if for all b there is an a, then there exists an h depending on I, such that this containment is true. And she had proved this in much more generality. Her rings did not have to be regular. What this theorem is telling us is that over a regular ring, we know exactly what that h is. It's the big height. And in fact, it can then be taken to be something that actually doesn't depend on I. Whether or not such a D, that will not be the dimension anymore, whether or not such a D independent of I exists, say for all primes in a more general ring is still an open question. That's been studied by many people, and there are many results about that, but I won't go into that. It's a fascinating question. I think out of the corner of my eye, I saw a question in the chat. That's right. So the second containment does not depend on anything about I and is true for all ideals. That's absolutely true. Yeah. So what's amazing about this is exactly that, right? It doesn't depend on I at all. It's uniform. It depends only on R. Okay, so we're getting to the point where I can finally write to you this Harbourne's conjecture in my title. So I took half the talk to get to here to give you a little bit of the story, and I'll take the second half of the talk to give you this survey on this conjecture. So Harbourne's conjecture is a proposed tightening of this containment. Harbourne asked, can we always do better? Could we, over a regular ring, can we take Hn and always subtract H minus 1 from it and get this containment? And in part, this is an extension. So one of the reasons why you would ask this is an extension of a question of unikeys. back from 2000 that is still open. Let's say that P is a prime in a regular local ring of height 2. He asks if the third symbolic power is contained in the square. So maybe it helps to do a little bit of numerology here. So for example, if you think about that prime from early on from our example, that prime that defines the curve that I'm just going to write, t cubed, t fourth, t fifth, that's a prime of height 2. So for primes, of course, the big height is the height. It is 2. And so the theorem says, for this case, it says that the 2n symbolic power is contained in the nth power for all n. So in particular, it says that the fourth symbolic power is contained in the square. We did see that the second symbolic power is not contained in the square. So from the perspective of giving a best possible answer to the containment problem, finding the smallest a possible, when you start off from 2, right? If you really want to answer what's the smallest number I can put here, you just want to decide what happens for 3. And I claimed earlier without proof, I just told you and you hopefully believed me, that in this case, in fact, the third symbolic power is indeed contained in the square. And by the way, I wanted to make this comment earlier, maybe I'll make it now. So here's a fun fact about curves like this one. The symbolic Riesz algebra so I said earlier that a symbolic Riesz algebra of an ideal is not always finitely generated, not always an Noetherian ring. And I'm writing here a vague statement to tell you the following. If you look at all the primes that define curves of the form t to the a, t to the b, t to the c for different values of a, b, c. Back in the 80s and the 90s, there was a big effort into trying to understand, well, first of all, the original question is the symbolic Riesz algebra always finally generated? And it was not, right? And then there were good reasons to think that at least for the primes defining these curves, that could still be true. And it turns out that these curves exhibit all sorts of strange behavior. And, you know, by work on many, many people that I couldn't possibly list them all now, so maybe I won't try, and I apologize to them. But by the work of many, many people, maybe, for example, I don't know, Dale Kokoski, Hema Srinivasan, Craig Hunicke. These are people that gave theorems, that gave conditions on ABCs that would make these curves not finitely generated. And then there's work of many other people giving examples of ABCs where these are not finitely generated. And when these do give finitely generated symbolic Riesz algebras, the degrees in which the symbolic Riesz algebra are generated in can be very different. And so in this family alone, you're going to find all sorts of strange behavior. So I would say if you're ever looking for bad behavior of symbolic powers, I would say look at this family first. This is a good place to look for funny behavior. And in fact, this is a class where I know that the answer to Hunicke's question is the third symbolic power in the square. I know the answer is yes, at least in characteristic not 3, by a theorem of mine. But Harbourne's conjecture is asking for something more. Right? It's asking for all n, can I always subtract a little bit from this hn the theorem gave me? And one very good reason, I think, why you would believe Harbourne's conjecture is the following. So let me give you a remark. Suppose you're in characteristic P, prime characteristic. over a field of prime characteristic. And you might remember earlier, I said that Hawkes and Hunicke proved that nice, beautiful theorem in characteristic P, and then used reduction to characteristic P to get it over fields of characteristic 0. But at the heart of their proof is a surprisingly elementary fact, which is the following. Suppose you take not any n you want, but a power of your characteristic. And you go and look at the HQ symbolic power of your ideal I. Turns out that is indeed contained in the Qth power, but in fact, you can do even better. It's containing the Qth Frobenius power. And somehow, this containment is the main ingredient you're going to need to prove this nice, beautiful theorem in characteristic P, but also that this containment on its own, in some way, completely reduces to essentially the pigeonhole principle. So I like to say that this is my favorite version of the pigeonhole principle. It's beautifully elementary that this is true. And if you go look at the proof carefully, you will notice that if you apply the pigeonhole principle in a best possible setting, right? If you do go to the extreme point of what the pigeonhole principle says, it actually gives you that you can subtract an h minus 1 here. So what I'm telling you is in characteristic P, Harbourne's conjecture is true for n's that are actually powers of your characteristic. So there are infinitely many values of n in characteristic P for which this containment is true. And one would naturally hope that you can then push this to get all values of n. Hawkes and Hunicke used that even without adding this, they went from Q to all n. So you could hope that I could use this containment to go from Q to all n. And the bizarre thing is that you can't. And the reason you can't is not that you can't, right? Is that none of us can. Because as I already spoiled this in the very beginning of the talk, Harbourne's conjecture is not true in this full generality. So I'm going to show you a family of examples that includes the very first counterexample to Harbourne's conjecture. That was given by Dumnitsky, Schomburg, and Tatagozinska back in 2013 is the publishing year. Their example was over C. It was 12 points in P2. And then Harbourne and Secelianu took their original example and noticed that it was part of a whole family of examples. So what I wrote here is this family of examples. These are all counterexamples to Harbourne's conjecture. We're in a situation where we have a radical ideal of height 2, of big height 2 as well. This is a pure height ideal. And since H is 2, this 3 and 2 is the very first instance of Harbourne's conjecture. I do want to say, though, these are not prime ideals, right? These have many components. And besides these examples, in the years that followed, many other people have worked hard on understanding both this original family and others that have been found since. And I could spend the remaining 20 minutes that I have just telling you about counterexamples, and I still wouldn't tell you all the very interesting research that is out there about counterexamples. There are many people whose names I should cite here. But I'm going to instead focus most of my time on the other side of the coin, not on the counterexamples, but on what I think is what makes those counterexamples so interesting. And the reason I personally think they're very interesting counterexamples is that I think of them, besides the fact that I just told you there are many families. Well, maybe the word many sounds too strong, but there are several, right? Despite that, I think those counterexamples are rare. And I think that many reasonable families of ideals satisfy this conjecture. But so even though I won't spend much more time on counterexamples, I do want point out at least one paper that I think is very interesting. So Ben Drapkin and Alexandra Siciliano, I think I looked yesterday, I think this is now 2020. So these original examples, these are 2x2 minors of some special 2x3 matrices. And they also, these are things that sort of arise as the singular locus of certain reflection arrangements. And what they did was they studied a whole family of such things that include these and completely decided among that family which ones are counterexamples to the conjecture and which ones are not. And in some sense, one of the things that they find, in fact, they're following work of other people. So they're sort of they're uniformizing work of various others. One of the things that they find is that there's sort of somehow it seems like symmetry plays some important role in this story. But instead, as I said, I want to tell you about positive statements. I want to tell you that I think the conjecture is mostly true. And in part, that's what makes these examples so interesting. So let me tell you about cases when the conjecture does hold. And I think the moral here is, if your ideal is nice enough, then the conjecture holds. So here are some cases. And actually, let me look at the time, make a quick decision here. Okay, I don't mean to scare you, but I'm going to just show you a pre-written list of examples so that I have time to tell you a bit more about something else in the story. So first of all, oh, no, I went too far. No, sorry, ignore that. That was not the right list. Oh, I thought I had it here. Okay, then I'm going to have to write it out. So let me tell you, sorry about that. Spoiler alert. I hope you didn't pay too much attention to what was written there yet. Okay, so it does hold if I define general points in P2, and that's a result of Bocci and Harbourne. Oops. And P3. And that's the result of Dumnichki. It also holds for various special configurations of points and arrangements of hyperplanes and various other things. For example, this one I'm just going to say out loud. Theorem of Jeremita, Harbourne, Mirori, and Nagel says it holds for a Metroid configuration. There's various other special configurations like that to say. It also holds for monomial ideals. And the case of monomial ideals is actually a sort of revamping of this thing I'd said up here about characteristic P. So it's a very similar story to this application of the pigeonhole principle. So somehow for monomial ideals, this isn't so hard to prove. But it turns out the monomial ideals are a subcase of a much larger family of examples of ideals that satisfy Harborne's conjecture. And that's the case when R mod I, so when the ring that I defines has nice singularities is the message here. When it's something called F pure in characteristic P, or of dense F pure type in characteristic 0. This is a result of myself and Craig Huneke. And rather than defining what F pure means, I'm just going to say it's some condition on the Frobenius map. You want, if your ring is F finite, so if the Frobenius map is a finite map, you want that the Frobenius map splits. Very quickly saying that's what it means. But let me instead give you examples if you don't think about these things very often. So it's a conditioning characteristic P, and it's a conditioning characteristic P that you can reduce to characteristic P to get results about, and characteristic 0 as well. So here are some examples of things. Well, one example, of course, is the case of monomial ideals. And I just realized I'm missing a word. Okay, so in some sense, it's true for all monomial ideals, but considering I'm only talking about radical things today, I should add in the word square free. So here's some examples of F pure things. If your ideal I is the ideal of T by T minors of a generic matrix. So take a matrix of variables of whatever size you want and take all the minors of a fixed size. The ideal that you get is an ideal that satisfies Harbourne's conjecture. Take an ideal that defines a Veronese ring. So the R mod I is the algebra generated over your field by all the monomials in a fixed number of variables of a fixed degree. It also is true for, maybe let me say, when R mod I is a nice, let me put nice in quotes, ring of invariance. So here by nice, I mean the usual stuff. I mean that I want the ring of invariance of a linearly reductive group. And it's true for many other things. So these are some examples that I think of as examples of nice, mild singularities. So what's being asked here is that, as I said before, right, you're asking for some level of niceness out of your ideal I. And let me make a quick time decision here. Maybe I'll say this out loud quickly. You can even do better. If you ask more of R mod I, so this is a theorem of myself and Greg Hunicke on the same paper. If R mod I is what is called strongly F regular, so it's also a characteristic P condition. Maybe let me say that's SFR. And for examples, all the things down here are strongly F regular, actually. So that's more than F pure. But your square free monomial ideals are not strongly F regular unless they're generated by variables. So it's a stronger condition. Let me just say it like this. I'm going to write a somewhat vague statement. You can replace H by H minus 1 in Harbourne's conjecture. So basically, if your ideal is nice enough, it behaves as if its big height is 1 less. So what I mean is, you look at the containment. Uh-oh, I've gone too far, haven't I? Oh, there it is. I'm so sorry. You look at the containment up here, and you write the same statement, but where you would have put H, you put H minus 1 instead. So notice in particular, when you would have plugged in 2, so if you have, say, a prime of height 2 that defines something strongly F regular, instead of 2, you put in a 1. But if you plug in H equal to 1 and you stare at this for a second, that actually is going to give you equality. So in particular, a theorem says if R mod I is really nice, so when H is 2, in that special case, this gives me equality of symbolic and ordinary powers for all n. So sometimes you can, not only is Harbourne's conjecture true, you can even do better if your ideal is nice enough. So what I want to do with the rest of my time is I want to tell you of a variation on Harbourne's conjecture that is still open and that some of us, maybe I'll say I at least, still believe is true. And that variation is what we're calling the stable Harbourne conjecture. I took the containment from Harbourne's conjecture, and I realized, well, I have examples where this fails for special values of n. But if you just sit down and start computing examples on your own, I think you're going to get an intuition that as n grows, the type of containments you're going to see get better. And you will hopefully start to wonder, if you make your n get really big, if n is sufficiently large, can this containment be true? And now this is the thing that I accidentally spoiled earlier. So here's a laundry list of cases where I know that this stable Harbourne conjecture holds. And in particular, I know that this stable Harbourne conjecture holds for all known counterexamples of the original conjecture. And when I say known, I should say known to me. But I think it's if there are new counterexamples I don't know of, I think they'll be very recent. And I'm going to tell you exactly why I know this is true for all known counterexamples of the original conjecture. So, in fact, for that first family of counterexamples, I'm going too far again, right here. For this family, it fails when n is 2. But it's true, this is what our one conjecture says, for all other values of n, for all n at least 3. I know this is true. So it fails in the beginning and then things get better. And that's what the stable conjecture is asking for. I also know it's true for space monomial curves. But for that bad class that I mentioned earlier, that would be a first place to look at for bad behavior. And I know it's true in all characteristics but 3, just for technical reasons. I'm not saying I just don't know what happens in characteristic 3. We need a different proof. That's the theorem of myself and Unique and Mukundan. And I'm also going to tell you a little bit about where this comes from. And then here's some more technical looking cases. So first of all, maybe I should have written these in a different order. Is true when I defines a general set of points in projective space, though I need an algebraically closed field to do that. That's a joint work with the Sankinil Bisui, Tai Han, Tai Nguyen. And then it's also true modulo some technical conditions. It's true for ideals defining Gorenstein rings and for homogeneous ideals generated in small degrees. The technical details are the following. All this comes from applying a theorem that I'm going to tell you soon that requires that your symbolic powers are computed by saturating with the maximal ideal. So this really means that the only potential embedded prime of all the powers is the maximal ideal. So for example, if you have a prime of height 1 less than the dimension, this is such a situation. For points, this is such a situation. In the case of I defining a Gorenstein ring, I need either characteristic to be, I need positive characteristic, or I need the symbolic with algebra to be finitely generated. Okay, so how do I know all these things? Well, there's lots and lots to say here, but I'm going to tell you about, in the 5 minutes that I have, I'm going to tell you about 2 of the main tricks that I know to do this. So the first trick I want to tell you about is something using the resurgence. So this is the resurgence of I defined by Bocci and Harbourne. And it's the supremum of the set of all quotients between numbers for which the containment does not hold. And notice that by Ein, Lazarsfeld-Smith, Hoxer-Hunicke, and Matt-Schweid, I know this is at most the big height. And by the way, is at least 1. Right, you cannot possibly have containments if A is smaller than B. And it turns out it's a very simple fact that I think I have time to explain. I see that I have 4 minutes, so I think I have time to explain this. That if the resurgence of I takes any value out there in the world you want, except for the maximum possible, if it is not actually H, if it's anything else, then the thing that you want is true. And why the thing that you want is you want that the hn minus h plus 1 symbolic power is in the nth power for some n. Well, actually you want it for all n large, but let's say you wanted to find it for a specific n. That would happen if the quotient between these two numbers was bigger than the supremum of all the quotients where the containment isn't true, right? So whenever this inequality is true, if you happen to know the resurgence, which by the way, you can sometimes compute without actually solving the containment problem, you can relate it to other invariants of your ideal. If you can explicitly know how much it is, you could find lots of containments that are true. But if you rewrite this is asking if n is more than h minus 1 over h minus the resurgence. And as long as this is not 0, which is my assumption right now, this is a number that makes sense. So you just compute how much this is. Like maybe it's 5,000. But now you know that for all n's bigger than 5,000, you have the containment you want. The reason we know Harbourne's conjecture for so many examples is that their resurgences have been computed via other methods besides solving the containment problem. There is no known example of an ideal whose resurgence is equal to the big height. And even if one existed, it still doesn't mean that stable Harbourne is false. So what you might try to do to solve this problem is you might try to prove that the resurgence of your ideal is strictly smaller than the big height. That's what we're calling ideals of expected resurgence, because we expect that the resurgence is anything but the big height. And let me end with a theorem in joint work with Craig Hunicke and Vivek Mukundan. I think it's now 2020. And the theorem says the following. Suppose you have a local or graded ring, right? So in the graded case, M is the homogeneous maximum ideal. And that you happen to know that the symbolic powers are computed by saturating with the maximum ideal. There's also a theorem without this assumption, but it looks a lot more technical. Suppose you proved the containment in Harbourne's conjecture for one special n. So for some n. Before I finish writing the theorem, let me tell you what I dreamed this theorem was, and then I'll correct it to what it really is. I dream we could show that if you prove, the containment Harbourne's conjecture once, then you would prove the resurgence is expected, which of course implies stable Harbourne. This is not quite our theorem though. You have to add a little m in here, which says you prove this containment, but in fact, there is no element in the symbolic power that is a minimal generator of the power. Once you do that, you've shown that the resurgence of your ideal is expected and the stable Harbourne holds. So let me use my last few seconds to say the following. So the moral of the story here is the conjecture isn't completely true as originally stated, but its counterexamples are very interesting because they're rare and difficult to find. And really because the original conjecture still holds for many classes of ideals. The original conjecture is still open for prime ideals, at least things that stay prime, after you complete. And more importantly, the stable version of the conjecture is open. And the evidence that it should be true in general keeps growing. I don't know if it's true or not, but I suspect it is. Thank you so much for your attention.
Thank you, Eloísa. We will take questions.
Excuse me, would you explain H replaced by H minus 1?
You mean what I wrote over here?
Yeah,
you mean this?
But both Hn minus H plus 1, two H's appear in this equation. So
Yeah.
both H's are replaced by H minus 1? Thank you.
Oh, I see what you mean. You mean this theorem with Craig Unique over here. Is this what you mean? This one here?
Yes.
Yes. So, okay. So really, everywhere you see H, you plug in H minus 1 instead. So I mean this. H minus 1 N. H minus 1 plus 1 containing I to the N.
Oh, thank you.
Yeah, that's what I meant. I was saying this quickly, because I wanted to say so many things, but I do realize it wasn't very clear. So I really mean the following. I mean that your ideal is going to satisfy the containment that an ideal with big height 1 less would have satisfied. That's what I mean. So in particular, an ideal of big height 2 behaves like one of height 1, for whom the equalities are it's actually all an equality, right? You have equality between all the symbolic powers and the powers.
Thank you.
Good question. Thank you.
Yeah, there's a question in chat box by Hassan. You can read the question.
Still can be
Yeah,
in particular. That is an ideal of 5 point. Okay, so let's see. First, there are many results I mentioned. I realized. So the Einlöser-Feld-Smith-Hoxter-Unique-Mass-Schwedt theorem is still true, and H is still the big height. Okay. You can. Well, I was going to say you can also replace H by other things, but yeah, this is still true as stated if I is just some ideal. And so this story here did not read radical at all. And the proof is essentially the same, right? In these things, usually what typically happens is once you understand the case of radical ideals, or at least, if you're proving a theorem for general ideals, once you prove the statement for radical ideals, the non-radical case, the changes you have to make in your technical details are typically always the same. So this theorem is still true. Some of the other things I said, however, really require radicals. So for example, this theorems with Craig Unique about F pure and strongly F regular rings or ideals that define such things. These do require radical, in particular because these conditions automatically imply reduced. So here, this is not saying anything about non-radical things. Now, how about fat points? There are, in fact, some results for fat points. So, for example, if I'm remembering the story right, stable Harbourne. So Yushi and Stefan Tohanehano have a couple of papers on these things. And in one of them, they show, I'm not going to cite I'm afraid I'm going to fail one of their assumptions, but they prove some results about certain sets of fat points satisfying stable Horborne. What else do I know? Definitely the questions all still make sense. And I'll have to think a little bit to tell you everything I may know about fat points. But the questions definitely make sense, and there's definitely some results about things like fat points. I hope I answered your question. is the containment true periodically? So let's see, do you mean like for all n's equal to, I don't know, maybe there's a function of, sorry?
For example, all even integers, all odd, or maybe of the form 4k plus 1, like that. So
Yeah, it's a good question. That's a very good question.
yeah.
So there are definitely situations where there are definitely ideals where when you want to describe their symbolic powers, I can think of families where, well, for example, of course, if the symbolic algebra is Noetherian, right, and generated in some low degree, right, you're going to describe your higher symbolic powers in a sort of periodic way. And so you could then study the containment. I would expect that you could study it, like separating in periodic cases. The closest thing that I know of that's true for big classes, the most general thing that comes to mind is not quite periodic in that sense, is the fact that in characteristic P, I know that Harbourne's conjecture is true for powers of your characteristic, right? That's not quite periodic, right? But it's still, there's an infinite family of values of n,
Yes.
for which is true. That's the closest thing to that I can think of.
Okay.
Besides this, I can't think of any other result that I know of that says, for all things of this type. Most results I know of are giving sufficient conditions for you to actually know that it's true after a certain point. And there are other results I did not mention that give you sufficient conditions to test something that guarantees that after a certain point you have equality always. There are several results of that kind. So maybe a little better than periodic, right? I guess you could think of that as periodic, right? You would think like the first however many you don't know, and then it's true, right? That could be your period, but otherwise, yeah. Good question.
Yeah, thank you.
You're welcome. Thank you.
Yeah, Eloísa, in one of the conditions you mentioned that if R mod I is strongly F regular, then the conjecture is true. So do we know whether it is false when R mod I is F rational?
I don't know. So here's what happens here. Behind the proof of these theorems, what is behind this is, so behind the F pure statement is something called Fetters Criterion. And Fetters Criterion tells you something about, okay, so here's a different, I guess if you like, you can think of this as a different condition that tells you what F purity means. So Fetters Criterion tells you that R mod I is F pure if for some Q or all large Q, this is true. And then there's something similar to this called Glass-Brenner's criterion that tells you when R mod I is strongly F regular. If, whatever F condition you want, if you have something similar to Fetters criterion that is equivalent to the condition you want, then I would strongly suspect that you can apply the same techniques and prove that the containment is true. Without such a criterion, I would not know how to attack the problem. Maybe another comment I will make is that there's this sort of informal principle that whenever you have something that's true for square free monomial ideals, it often generalizes to ideals defining F pure rings. There are many examples of this behavior, but I don't know about other conditions. I do know about rings that are not regular. There are theorems of this kind. So with Lynch-Rama and Carl Schweed, I have a paper on extending these results with Craig Hunicke to rings that are not regular. But I do not know about other characteristic P conditions. In particular, if you do not have a Fetter-like condition for it, I would not know how to attack the question.
In the case of T by T minors of a generic matrix, is the conjecture true in a characteristic free manner? In any characteristic?
Yeah. Yes, it is. Yes, it is.
Okay.
Yes, it is. So it's not just in characteristic P. You do the characteristic zero version by reducing to characteristic P. But yeah, it's true. So over any field.
Okay.
To make it clear. Yeah, absolutely. Good question.
All right.
So these examples here, you could take all of them. You could take these examples as they're all characteristic free. Also Veronese, also characteristic free. Over fields.
So how do people calculate resurgence?
Good question. Okay, so the trick is you give lower bounds and upper bounds, and you hope that they are equal. So here's what you do. Giving lower bounds is easy if you have some non-containment, right? You hand me a particular non-containment, it gives me a lower bound. To give upper bounds, there are some theorems that say the resurgence is always less or equal than this other invariant. So for example, you can always compare it to a quotient between something called the Waldschmidt constant and the regularity of I. And so the way people do this is sometimes you go and compute this upper bound and you go and compute some non-containments. And you find that you have a non-containment that gives you exactly the value of your upper bound. And then you're done. You completely computed the resurgence. And it turns out that for the known counterexamples to Harbourne's conjecture, it turns out that they are geometrically, they're very nice and very rich, and it's sort of easier to compute these things for them. And I don't mean that it's easy, right? I just mean that it's doable, versus studying some random thing out there. So that's the main way that people would compute resurgence. The dream for me is to give good lower bounds, right? If you prove that you have a particular lower bound that's always less than the big height, I would be happy, right? I would consider the problem solved if you could do that in, for any ideal.
Thank you.
However, yeah, thanks.
So is there a study on comparing powers of tight closure and ordinary powers?
Tight closure. Yeah, so I don't know if this is your question, but the way that Hoxton and Hunicke prove this theorem is what they actually prove. They prove that the symbolic power is contained in the tight closure of the power.
Okay.
That's what they actually prove. But then they're in a regular ring. And they're done.
Okay.
That's what they actually prove. So they do. That's why they need something with Frobenius powers.
Okay. Yeah.
Good
so
question. Yeah. So there is a containment that is true over other rings as well. It's just not with the powers.
Okay. Yeah. Thanks. Thank you very much.
Yeah. Thank you. Good question.
Right. So, are there any further questions? If not, let us all thank Eloísa for her very interesting talk.
Thank you.
Yeah.
Thank you for having me. This was fun.